In mathematics and computer science, an algorithm, I/ALRM/ALG, (READHM), is a self-contained step-by-step set of operations to be performed. Algorithms exist that perform calculation, data processing, and automated reasoning. An algorithm is an effective method expressed as a finite list of well-defined instructions for calculating a function. Starting from an initial state and initial input, perhaps empty, the instructions describe a computation that, when executed, proceeds through a finite number of well-defined successive states, eventually producing output and terminating at a final ending state. The transition from one state to the next is not necessarily deterministic. Some algorithms, known as randomized algorithms, incorporate random input. The concept of algorithm has existed for centuries. However, partial formalization of what would become the modern algorithm began with attempts to solve the Entscheidungsproblem, the decision problem posed by David Hilbert, in 1928. Subsequent formalizations were framed as attempts to define effective calculability or effective method. Those formalizations included the Gödel-Herbrand-Kleene recursive functions of 1930, 1934, and 1935, Alonzo Church's lambda calculus of 1936, Emil Post's formulation 1 of 1936, and Alan Turing's Turing machines of 1936-7 and 1939. Giving a formal definition of algorithms corresponding to the intuitive notion remains a challenging problem. Word origin. Algorithm stems from the name of a Latin translation of a book written by Al-Khwarizm, a Persian mathematician, astronomer, and geographer. Al-Khwarizmi wrote a book titled On the Calculation with Hindu Numerals in about 825 AD, and was principally responsible for spreading the Indian system of numeration throughout the Middle East and Europe. It was translated into Latin as Algoritmi de Numero Indirum, in English, Al-Khwarizmi, on the Hindu art of reckoning. The term algoritmi in the title of the book led to the term algorithm. Informal definition. For a detailed presentation of the various points of view around the definition of algorithm, see algorithm characterizations. An informal definition could be a set of rules that precisely defines a sequence of operations, which would include all computer programs, including programs that do not perform numeric calculations. Generally, a program is only an algorithm if it stops eventually. A prototypical example of an algorithm is Euclid's algorithm to determine the maximum common divisor of two integers. An example, there are others, is described by the flowchart above and as an example in a later section. Bliss and Jeffrey, 1974-1999, offer an informal meaning of the word in the following quotation. No human being can write fast enough, or long enough, or small enough, smaller and smaller without limit. You'd be trying to write on molecules, on atoms, on electrons to list all members of an innumerably infinite set, by writing out their names, one after another, in some notation. But humans can do something equally useful. In the case of certain innumerably infinite sets, they can give explicit instructions for determining the nth member of the set, for arbitrary finite, and such instructions are to be given quite explicitly, in a form in which they could be followed by a computing machine, or by a human, who is capable of carrying out only very elementary operations on symbols. An innumerably infinite set is one whose elements can be put into one-to-one correspondence with the integers. Thus, Bliss and Jeffrey are saying that an algorithm implies instructions for a process that creates output integers from an arbitrary input integer or integers that, in theory, can be arbitrarily large. Thus an algorithm can be an algebraic equation such as y equals m plus n to arbitrary input variables m and n, that produce an output y, but various authors' attempts to define the notion indicate that the word implies much more than this, something on the order of, for the addition example, precise instructions, in language understood by the computer for a fast, efficient, good process that specifies the moves of the computer machine, or human, equipped with the necessary internally contained information and capabilities to find, decode, and then process arbitrary input integers /symbols m and n, symbols, plus, and equals, and effectively produce, in a reasonable time, output integer y, at a specified place and in a specified format. The concept of algorithm is also used to define the notion of decidability. That notion is central for explaining how formal systems come into being, starting from a small set of axioms and rules. In logic, the time that an algorithm requires to complete cannot be measured, as it is not apparently related with our customary physical dimension. From such uncertainties that characterize ongoing work stems the unavailability of a definition of algorithm that suits both concrete, in some sense, and abstract usage of the term. Formalization. Algorithms are essential to the way computers process data. Many computer programs contain algorithms that detail the specific instructions a computer should perform, in a specific order, to carry out a specified task, such as calculating employees' paychecks, or printing students' report cards. Thus, an algorithm can be considered to be any sequence of operations that can be simulated by a Turing complete system. Authors who assert this thesis include Minsky, 1967, Savage, 1987, and Gurevich, 2000. Minsky, but we will also maintain, with Turing, that any procedure which could naturally be called effective, can in fact be realized by a simple machine. Although this may seem extreme, the arguments in its favor are hard to refute. Gurevich, Turing's informal argument in favor of his thesis justifies a stronger thesis. Every algorithm can be simulated by a Turing machine. According to Savage 1987, an algorithm is a computational process defined by a Turing machine. Typically, when an algorithm is associated with processing information, data is read from an input source, written to an output device, and /or stored for further processing. Stored data is regarded as part of the internal state of the entity performing the algorithm. In practice, the state is stored in one or more data structures. For some such computational process, the algorithm must be rigorously defined, specified in the way it applies in all possible circumstances that could arise. That is, any conditional steps must be systematically dealt with, case by case. The criteria for each case must be clear and computable. Because an algorithm is a precise list of precise steps, the order of computation is always critical to the functioning of the algorithm. Instructions are usually assumed to be listed explicitly, and are described as starting from the top and going down to the bottom, an idea that is described more formally by flow of control. So far, this discussion of the formalization of an algorithm has assumed the premises of imperative programming. This is the most common conception, and it attempts to describe a task in discrete, mechanical means. Unique to this conception of formalized algorithms is the assignment operation, setting the value of a variable. It derives from the intuition of memory, as a scratchpad. There is an example below of such an assignment. For some alternate conceptions of what constitutes an algorithm, see functional programming and logic programming. Expressing algorithms. Algorithms can be expressed in many kinds of notation, including natural languages, pseudocode, flowcharts, Dracon charts, programming languages, or control tables processed by interpreters. Natural language expressions of algorithms tend to be verbose and ambiguous, and are rarely used for complex or technical algorithms. Pseudocode, flowcharts, Dracon charts, and control tables are structured ways to express algorithms that avoid many of the ambiguities common in natural language statements. Programming languages are primarily intended for expressing algorithms in a form that can be executed by a computer, but are often used as a way to define or document algorithms. There is a wide variety of representations possible, and one can express a given Turing machine program as a sequence of machine tables. See more at finite state machine, state transition table, and control table. as flowcharts and Dracon charts, see more at state diagram, or as a form of rudimentary machine code or assembly code called sets of quadruples, see more at Turing machine. Representations of algorithms can be classed into 3 accepted levels of Turing machine description. 1. High-level description. Pros to describe an algorithm, ignoring the implementation details. At this level we do not need to mention how the machine manages its state or head. 2. Implementation description. Pros used to define the way the Turing machine uses its head, and the way that it stores data on its tape. At this level we do not give details of states or transition function. 3. Formal description. Most detailed, lowest level gives the Turing machine's state table. For an example of the simple algorithm add m plus n described in all 3 levels, see algorithm examples. Implementation. Most algorithms are intended to be implemented as computer programs. However, algorithms are also implemented by other means, such as in a biological neural network, for example, the human brain implementing arithmetic, or an insect looking for food, in an electrical circuit, or in a mechanical device. Computer algorithms. Flowchart examples of the canonical Bohm-Jacobini structures, the sequence, rectangles descending the page, the while do, and the if then else. The 3 structures are made of the primitive conditional goto, if test equals true then goto step xxx, a diamond, the unconditional goto, rectangle, various assignment operators, rectangle, and halt, rectangle. Nesting of these structures inside assignment blocks result in complex diagrams, compare Tosworth 1977 100114. In computer systems, an algorithm is basically an instance of logic written in software by software developers to be effective for the intended target computer, for the target machines, to produce output from given input, perhaps null. An optimal algorithm, even running in old hardware, would produce faster results than a non-optimal, higher time complexity algorithm, for the same purpose, running in more efficient hardware. That is why the algorithms, like computer hardware, are considered technology. Elegant compact programs, good fast programs. The notion of simplicity and elegance appears informally in Knuth, and precisely in Chaitin. Knuth. We want good algorithms in some loosely defined aesthetic sense. One criterion is the length of time taken to perform the algorithm. Other criteria are adaptability of the algorithm to computers, its simplicity and elegance, etc. Chaitin. A program is elegant, by which I mean that it's the smallest possible program for producing the output that it does. Chaitin prefaces his definition with, I'll show you can't prove that a program is elegant. Such a proof would solve the halting problem, IBID. Algorithm versus function computable by an algorithm. For a given function multiple algorithms may exist. This is true, even without expanding the available instruction set available to the programmer. Rogers observes that it is important to distinguish between the notion of algorithm, i.e., procedure, and the notion of function computable by algorithm, i.e. mapping yielded by procedure. The same function may have several different algorithms. Unfortunately, there may be a trade-off between goodness, speed, and elegance, compactness. An elegant program may take more steps to complete a computation than one less elegant. An example that uses Euclid's algorithm appears below. Computers and computers. Models of computation. A computer, or human computer, is a restricted type of machine, a discrete deterministic mechanical device that blindly follows its instructions. Melzak's and Lambek's primitive models reduce this notion to 4 elements: I, discrete, distinguishable locations; I, discrete, indistinguishable counters; I, an agent; and IV, a list of instructions that are effective relative to the capability of the agent. Minsky describes a more congenial variation of Lambek's abacus model in his very simple basis for computability. Minsky's machine proceeds sequentially through its 5 or 6, depending on how one counts, instructions, unless either a conditional if-then goto or an unconditional goto changes program flow out of sequence. Besides halt, Minsky's machine includes 3 assignment, replacement, substitution, operations, 0, e.g. the of location replaced by L0, successor, e.g. LL, +1, and decrement, e.g. LL1. Rarely must a programmer write code with such a limited instruction set. But Minsky shows, as do Melzack and Lambeck, that his machine is Turing complete with only 4 general types of instructions: conditional goto, unconditional goto, assignment/replacement/substitution, and halt. Simulation of an algorithm, computer, language. Knuth advises the reader that the best way to learn an algorithm is to try it. Immediately take pen and paper and work through an example. But what about the simulation or execution of the real thing? The programmer must translate the algorithm into a language that the simulator/computer can effectively execute. Stone gives an example of this. When computing the roots of a quadratic equation, the computer must know how to take a square root. If they don't, then for the algorithm to be effective, it must provide a set of rules for extracting a square root. This means that the programmer must know a language that is effective relative to the target computing agent, computer/computer. But what model should be used for the simulation? Van de Bois observes, even if we base complexity theory on abstract instead of concrete machines, arbitrariness of the choice of the model remains. It is at this point that the notion of simulation enters. When speed is being measured, the instruction set matters. For example, the subprogram in Euclid's algorithm to compute the remainder would execute much faster if the programmer had a modulus division instruction available rather than just subtraction, or worse, just Minsky's decrement. Structured programming. Canonical structures, per the Church-Turing thesis, any algorithm can be computed by a model known to be Turing complete, and per Minsky's demonstrations, Turing completeness requires only 4 instruction types: conditional goto, unconditional goto, assignment, halt. Kemeny and Kurtz observe that while undisciplined use of unconditional gotos and conditional if-then gotos can result in spaghetti code, a programmer can write structured programs using these instructions. On the other hand, it is also possible, and not too hard, to write badly structured programs in a structured language. Tosworth augments the 3 Bohm-Jacobini canonical structures, sequence, if-then-else, and while-do, with 2 more, do-while and case. An additional benefit of a structured program is that it lends itself to proofs of correctness using mathematical induction. Canonical flowchart symbols. The graphical aid called a flowchart offers a way to describe and document an algorithm and a computer program of one. Like program flow of a Minsky machine, a flowchart always starts at the top of a page and proceeds down. Its primary symbols are only 4: the directed arrow showing program flow, the rectangle, sequence, goto, the diamond, if-then-else, and the dot, or tie. The Bohm-Jacobini canonical structures are made of these primitive shapes. Substructures can nest in rectangles, but only if a single exit occurs from the superstructure. The symbols and their use to build the canonical structures are shown in the diagram. Examples. Further information, algorithm examples. Algorithm example. An animation of the quicksort algorithm sorting an array of randomized values. The red bars mark the pivot element. At the start of the animation, the element farthest to the right-hand side is chosen as the pivot. One of the simplest algorithms is to find the largest number in a list of numbers of random order. Finding solution requires looking at every number in the list. From this follows a simple algorithm, which can be stated in a high-level description English prose as high-level description. 1. If there are no numbers in the set, then there is no highest number. 2. Assume the first number in the set is the largest number in the set. 3. For each remaining number in the set, if this number is larger than the current largest number, consider this number to be the largest number in the set. 4. When there are no numbers left in the set to iterate over, consider the current largest number to be the largest number of the set. quasi-formal description, written in prose, but much closer to the high-level language of a computer program. The following is the more formal coding of the algorithm in pseudocode or pigeon code. Algorithm: largest number input, a list of numbers L. Output: the largest number in the list L. If L size equals 0, return null largest L0 for each item in L. Do if item largest, then largest item return largest. Is a shorthand for changes to. For instance, largest item means that the value of largest changes to the value of item. Return terminates the algorithm and outputs the value that follows. Euclid's algorithm. Further information, Euclid algorithm. The example diagram of Euclid's algorithm from T.L. Heath 1908, with more detail added. Euclid does not go beyond a third measuring and gives no numerical examples. Nicomacheus gives the example of 49 and 21. I subtract the less from the greater, 28 is left, then again I subtract from this the same 21, for this is possible, 7 is left, I subtract this from 21, 14 is left, from which I again subtract 7, for this is possible, 7 is left, but 7 cannot be subtracted from 7. Heath comments that the last phrase is curious, but the meaning of it is obvious enough, as also the meaning of the phrase about ending at one and the same number. Heath 1908 300. Euclid's algorithm appears as Proposition 2 in Book 7, Elementary Number Theory, of his Elements. Euclid poses the problem, given two numbers not prime to one another, to find their greatest common measure. He defines a number to be a multitude composed of units, a counting number, a positive integer not including 0. And to measure is to place a shorter measuring length S successively, Q times, along longer length L, until the remaining portion R is less than the shorter length S. In modern words, remainder R equals LQ star S, Q being the quotient, or remainder R is the modulus, the integer fractional part left over after the division. For Euclid's method to succeed, the starting lengths must satisfy two requirements: I, the lengths must not be 0, and I, the subtraction must be proper. A test must guarantee that the smaller of the two numbers is subtracted from the larger. Alternately, the two can be equal so their subtraction yields 0. Euclid's original proof adds a third: the two lengths are not prime to one another. Euclid stipulated this so that he could construct a reductio ad absurdum proof that the two numbers' common measure is in fact the greatest, while Nicomacheus' algorithm is the same as Euclid's. When the numbers are prime to one another, it yields the number 1 for their common measure. So to be precise, the following is really Nicomacheus' algorithm. A graphical expression on Euclid's algorithm using example with 1599 and 650. 1599 equals 650 times 2, plus 299 650 equals 299 times 2, plus 52 299 equals 52 times 5, plus 39 52 equals 39 times 1, plus 13. 39 equals 13 times 3, plus 0. Computer language for Euclid's algorithm. Only a few instruction types are required to execute Euclid's algorithm: some logical tests, conditional goto, unconditional goto, assignment, replacement, and subtraction. A location is symbolized by uppercase letter S, e.g. S, A, etc. The varying quantity, number, in a location is written in lowercase letter s, and, usually, associated with the location's name. For example, location L at the start might contain the number L equals 3009. An elegant program for Euclid's algorithm. An elegant is a translation of Knuth's version of the algorithm with a subtraction-based remainder loop replacing his use of division, or a modulus instruction. Derived from Knuth 1973-4. Depending on the two numbers, an elegant may compute the GCD in fewer steps than elegant. The following algorithm is framed as Knuth's four-step version of Euclid's and Nicomacheus, but rather than using division, to find a remainder it uses successive subtractions of the shorter length S from the remaining length R until R is less than S. The high-level description, shown in boldface, is adapted from Knuth 1973-4. Input. 1 into 2 locations L and S. Put the numbers L and S that represent the two lengths input L, S to initialize R. Make the remaining length R equal to the starting / initial / input length LRL. Ensure S. 3. Ensure the smaller of the two numbers is in S, and the larger in R. If R S then the of L is the larger number, so skip over the exchange steps 4, 5, and 6. Go to step 6, else swap the of R and S. For LR, this first step is redundant, but is useful for later discussion. 5 RS success E1, find remainder until the remaining length R in R is less than the shorter length S in S. Repeatedly subtract the measuring number S in S from the remaining length R in R. 7 if S are then done measuring, so go to 10, else measure again. 8 RRS 9 remainder loop, go to 7. E2 is the remainder 0 either I, the last measure was exact, and the remainder in R is 0, program can halt, or I, the algorithm must continue, the last measure left a remainder in R less than measuring number in S. 10 if R equals 0 then done, so go to step 15, else continue to step 11. E3, interchange S and R, the nut of Euclid's algorithm. Use remainder R to measure what was previously smaller number S. L serves as a temporary location. 11 LR 12 RS 13 SL 14. Repeat the measuring process, go to 7. Output 15 done. S contains the greatest common divisor, print S. Done. 16 halt, end, stop. An elegant program for Euclid's algorithm. The following version of Euclid's algorithm requires only 6 Go instructions to do what 13 are required to do by an elegant course. An elegant requires more types of instructions. The flowchart of elegant can be found at the top of this article. In the unstructured, basic language, the steps are numbered, and the instruction let equals is the assignment instruction symbolized by 5 rem. Euclid's algorithm for greatest common divisor. 6 print type 2 integers greater than 0. 10 input A, B 20. If B equals 0 then go to 80 30. If A B then go to 60 40. Let B equals B A 50, go to 20 60. Let A E equals A B 70, go to 20 80. Print A 90. End. How elegant works: in place of an outer Euclid loop, elegant shifts back and forth between two co-loops, an AB loop that computes AAB and a BA loop that computes BBA. This works because when at last the minuend M is less than or equal to the subtrahend S, difference equals minuend subtrahend, the minuend can become S, the new measuring length, and the subtrahend can become the newer length to be measured. In other words, the sense of the subtraction reverses. Testing the Euclid algorithms. Does an algorithm do what its author wants it to do? A few test cases usually suffice to confirm core functionality. One source uses 3009 and 884. Knuth suggested 40,902, 24,140. Another interesting case is the two relatively prime numbers 14,157 and 5,950. But exceptional cases must be identified and tested. Will an elegant perform properly when RS, SR, R equals S? Ditto for elegant BA, AB, AE equals B? Yes to all? What happens when one number is 0, both numbers are 0? An elegant computes forever in all cases. Elegant computes forever when AE equals 0. What happens if negative numbers are entered? Fractional numbers. If the input numbers, i.e. the domain of the function computed by the algorithm/program, is to include only positive integers including 0, then the failures at 0 indicate that the algorithm, and the program that instantiates it, is a partial function rather than a total function. A notable failure due to exceptions is the area and Vierocket failure. Proof of program correctness by use of mathematical induction. Knuth demonstrates the application of mathematical induction to an extended version of Euclid's algorithm, and he proposes a general method applicable to proving the validity of any algorithm. Tosworth proposes that a measure of the complexity of a program be the length of its correctness proof. Measuring and improving the Euclid algorithms. Elegance, compactness, versus goodness, speed. With only 6 Go instructions, Elegant is the clear winner compared to inelegant, at 13 instructions. However, inelegant is faster, it arrives at halt in fewer steps. Algorithm analysis indicates why this is the case. Elegant does 2 conditional tests in every subtraction loop, whereas inelegant only does 1. As the algorithm usually requires many loop-throughs, on average much time is wasted doing a b equals 0 test that is needed only after the remainder is computed. Can the algorithms be improved once the programmer judges a program fit and effective, that is, it computes the function intended by its author? Then the question becomes, can it be improved? The compactness of inelegant can be improved by the elimination of 5 steps. But Chaitin proved that compacting an algorithm cannot be automated by a generalized algorithm, rather, it can only be done heuristically, i.e., by exhaustive search. Examples to be found at Busy Beaver, trial and error, cleverness, insight, application of inductive reasoning, etc. Observe that steps 4, 5, and 6 are repeated in steps 11, 12, and 13. Comparison with elegant provides a hint that these steps together with steps 2 and 3 can be eliminated. This reduces the number of core instructions from 13 to 8, which makes it more elegant than elegant at 9 steps. The speed of elegant can be improved by moving the b equals 0 test outside of the 2 subtraction loops. This change calls for the addition of 3 instructions, b equals 0, a equals 0, go to. Now elegant computes the example numbers faster, whether for any given a, b, and r, s. This is always the case, would require a detailed analysis. Algorithmic analysis. Analysis of algorithms. It is frequently important to know how much of a particular resource, such as time or storage, is theoretically required for a given algorithm. Methods have been developed for the analysis of algorithms to obtain such quantitative answers. Estimates, for example, the sorting algorithm above has a time requirement of O, and, using the big O notation within, as the length of the list. At all times the algorithm only needs to remember 2 values, the largest number found so far, and its current position in the input list. Therefore it is said to have a space requirement of O1, if the space required to store the input numbers is not counted, or O(n) if it is counted. Different algorithms may complete the same task with a different set of instructions in less or more time, space, or effort than others. For example, a binary search algorithm usually outperforms a brute force sequential search when used for table lookups on sorted lists. Formal versus empirical. Empirical algorithmics, profiling, computer programming, and program optimization. The analysis and study of algorithms is a discipline of computer science and is often practiced abstractly without the use of a specific programming language or implementation. In this sense, algorithm analysis resembles other mathematical disciplines in that it focuses on the underlying properties of the algorithm and not on the specifics of any particular implementation. Usually pseudocode is used for analysis, as it is the simplest and most general representation. However, ultimately, most algorithms are usually implemented on particular hardware/software platforms, and their algorithmic efficiency is eventually put to the test using real code. For the solution of a one-off problem, the efficiency of a particular algorithm may not have significant consequences, unless it is extremely large, but for algorithms designed for fast interactive, commercial or long-life scientific usage it may be critical. Scaling from small into large and frequently exposes inefficient algorithms that are otherwise benign. Empirical testing is useful because it may uncover unexpected interactions that affect performance. Benchmarks may be used to compare before/after potential improvements to an algorithm after program optimization. Execution efficiency. Algorithmic efficiency. To illustrate the potential improvements possible even in well-established algorithms, a recent significant innovation relating to FFT algorithms, used heavily in the field of image processing, can decrease processing time up to 1,000 times for applications like medical imaging. In general, speed improvements depend on special properties of the problem, which are very common in practical applications. Speed-ups of this magnitude enable computing devices that make extensive use of image processing, like digital cameras and medical equipment, to consume less power. Classification. There are various ways to classify algorithms, each with its own merits. By implementation. One way to classify algorithms is by implementation means. Recursion or iteration. A recursive algorithm is one that makes reference to itself repeatedly until a certain condition, also known as termination condition, matches, which is a method common to functional programming. Iterative algorithms use repetitive constructs, like loops, and sometimes additional data structures, like stacks, to solve the given problems. Some problems are naturally suited for one implementation or the other. For example, Towers of Hanoi is well understood using recursive implementation. Every recursive version has an equivalent, but possibly more or less complex, iterative version, and vice versa. Logical. An algorithm may be viewed as controlled logical deduction. This notion may be expressed as algorithm equals logic plus control. The logic component expresses the axioms that may be used in the computation, and the control component determines the way in which deduction is applied to the axioms. This is the basis for the logic programming paradigm. In pure logic programming languages, the control component is fixed and algorithms are specified by supplying only the logic component. The appeal of this approach is the elegant semantics. A change in the axioms has a well-defined change in the algorithm. Serial, parallel or distributed. Algorithms are usually discussed with the assumption that computers execute one instruction of an algorithm at a time. Those computers are sometimes called serial computers. An algorithm designed for such an environment is called a serial algorithm, as opposed to parallel algorithms or distributed algorithms. Parallel algorithms take advantage of computer architectures where several processors can work on a problem at the same time, whereas distributed algorithms utilize multiple machines connected with a network. Parallel or distributed algorithms divide the problem into more symmetrical or asymmetrical subproblems and collect the results back together. The resource consumption in such algorithms is not only processor cycles on each processor, but also the communication overhead between the processors. Some sorting algorithms can be parallelized efficiently, but their communication overhead is expensive. Iterative algorithms are generally parallelizable. Some problems have no parallel algorithms and are called inherently serial problems. Deterministic or non-deterministic. Deterministic algorithms solve the problem with exact decision at every step of the algorithm, whereas non-deterministic algorithms solve problems via guessing, although typical guesses are made more accurate through the use of heuristics. Exact or approximate. While many algorithms reach an exact solution, approximation algorithms seek an approximation that is close to the true solution. Approximation may use either a deterministic or a random strategy. Such algorithms have practical value for many hard problems. Quantum algorithm. They run on a realistic model of quantum computation. The term is usually used for those algorithms which seem inherently quantum, or use some essential feature of quantum computation such as quantum superposition or quantum entanglement. By design paradigm. Another way of classifying algorithms is by their design methodology or paradigm. There is a certain number of paradigms, each different from the other. Furthermore, each of these categories include many different types of algorithms. Some common paradigms are brute force or exhaustive search. This is the naive method of trying every possible solution to see which is best. Divide and conquer. A divide and conquer algorithm repeatedly reduces an instance of a problem to one or more smaller instances of the same problem, usually recursively, until the instances are small enough to solve easily. One such example of divide and conquer is merge sorting. Sorting can be done on each segment of data after dividing data into segments, and sorting of entire data can be obtained in the conquer phase by merging the segments. A simpler variant of divide and conquer is called a decrease and conquer algorithm that solves an identical subproblem and uses the solution of this subproblem to solve the bigger problem. Divide and conquer divides the problem into multiple subproblems, and so the conquer stage is more complex than decrease and conquer algorithms. An example of decrease and conquer algorithm is the binary search algorithm. Search and enumeration. Many problems, such as playing chess, can be modeled as problems on graphs. A graph exploration algorithm specifies rules for moving around a graph, and is useful for such problems. This category also includes search algorithms, branch and bound enumeration, and backtracking. Randomized algorithm. Such algorithms make some choices randomly or pseudo-randomly. They can be very useful in finding approximate solutions for problems where finding exact solutions can be impractical. See Heuristic Method below. For some of these problems, it is known that the fastest approximations must involve some randomness. Whether randomized algorithms with polynomial time complexity can be the fastest algorithms for some problems is an open question known as the P versus NP problem. There are two large classes of such algorithms. 1. Monte Carlo algorithms return a correct answer with high probability. E.g., RP is the subclass of these that run in polynomial time. 2. Las Vegas algorithms always return the correct answer, but their running time is only probabilistically bound, e.g. ZPP. Reduction of complexity. This technique involves solving a difficult problem by transforming it into a better known problem for which we have, hopefully, asymptotically optimal algorithms. The goal is to find a reducing algorithm whose complexity is not dominated by the resulting reduced algorithms. For example, one selection algorithm for finding the median in an unsorted list involves first sorting the list, the expensive portion, and then pulling out the middle element in the sorted list, the cheap portion. This technique is also known as transform and conquer. Optimization problems. For optimization problems there is a more specific classification of algorithms. An algorithm for such problems may fall into one or more of the general categories described above as well as into one of the following. Linear programming. When searching for optimal solutions to a linear function bound to linear equality and inequality constraints, the constraints of the problem can be used directly in producing the optimal solutions. There are algorithms that can solve any problem in this category, such as the popular simplex algorithm. Problems that can be solved with linear programming include the maximum flow problem for directed graphs. If a problem additionally requires that one or more of the unknowns must be an integer, then it is classified in integer programming. A linear programming algorithm can solve such a problem if it can be proved that all restrictions for integer values are superficial, i.e., the solutions satisfy these restrictions anyway. In the general case, a specialized algorithm, or an algorithm that finds approximate solutions is used, depending on the difficulty of the problem. Dynamic programming. When a problem shows optimal substructures, meaning the optimal solution to a problem can be constructed from optimal solutions to subproblems, and overlapping subproblems, meaning the same subproblems are used to solve many different problem instances. A quicker approach called dynamic programming avoids recomputing solutions that have already been computed. For example, Floyd-Warshall algorithm, the shortest path to a goal from a vertex in a weighted graph can be found by using the shortest path to the goal from all adjacent vertices. Dynamic programming and memoization go together. The main difference between dynamic programming and divide and conquer is that subproblems are more or less independent in divide and conquer, whereas subproblems overlap in dynamic programming. The difference between dynamic programming and straightforward recursion is in caching or memoization of recursive calls. When subproblems are independent, and there is no repetition, memoization does not help, hence dynamic programming is not a solution for all complex problems. By using memoization, or maintaining a table of subproblems already solved, dynamic programming reduces the exponential nature of many problems to polynomial complexity. The greedy method. A greedy algorithm is similar to a dynamic programming algorithm, in that it works by examining substructures, in this case not of the problem, but of a given solution. Such algorithms start with some solution, which may be given, or have been constructed in some way, and improve it by making small modifications. For some problems they can find the optimal solution, while for others they stop at local optima, that is at solutions that cannot be improved by the algorithm, but are not optimum. The most popular use of greedy algorithms is for finding the minimal spanning tree, where finding the optimal solution is possible with this method. Huffman tree, Kruskal, Prim, Solon are greedy algorithms that can solve this optimization problem. The heuristic method. In optimization problems, heuristic algorithms can be used to find a solution close to the optimal solution. In cases where finding the optimal solution is impractical, these algorithms work by getting closer and closer to the optimal solution as they progress. In principle, if run for an infinite amount of time, they will find the optimal solution. Their merit is that they can find a solution very close to the optimal solution in a relatively short time. Such algorithms include local search, taboo search, simulated annealing, and genetic algorithms. Some of them, like simulated annealing, are non-deterministic algorithms, while others, like taboo search, are deterministic. When a bound on the error of the non-optimal solution is known, the algorithm is further categorized as an approximation algorithm. By field of study. See also, list of algorithms. Every field of science has its own problems and needs efficient algorithms. Related problems in one field are often studied together. Some example classes are search algorithms, sorting algorithms, merge algorithms, numerical algorithms, graph algorithms, string algorithms, computational geometric algorithms, combinatorial algorithms, medical algorithms, machine learning, cryptography, data compression algorithms, and parsing techniques. Fields tend to overlap with each other, and algorithm advances in one field may improve those of other, sometimes completely unrelated, fields. For example, dynamic programming was invented for optimization of resource consumption in industry, but is now used in solving a broad range of problems in many fields. By complexity. See also, complexity class and parameterized complexity. Algorithms can be classified by the amount of time they need to complete compared to their input size. There is a wide variety. Some algorithms complete in linear time relative to input size, some do so in an exponential amount of time, or even worse, and some never halt. Additionally, some problems may have multiple algorithms of differing complexity, while other problems might have no algorithms or no known efficient algorithms. There are also mappings from some problems to other problems. Owing to this, it was found to be more suitable to classify the problems themselves instead of the algorithms into equivalence classes based on the complexity of the best possible algorithms for them. Bergen, 2005, page 24, uses a generalized definition of algorithms that relaxes the common requirement that the output of the algorithm that computes a function must be determined after a finite number of steps. He defines a super-recursive class of algorithms as a class of algorithms in which it is possible to compute functions not computable by any Turing machine. Bergen, 2005, page 107. This is closely related to the study of methods of hypercomputation. Continuous algorithms. The adjective continuous when applied to the word algorithm can mean an algorithm operating on data that represents continuous quantities, even though this data is represented by discrete approximations. Such algorithms are studied in numerical analysis, or an algorithm in the form of a differential equation that operates continuously on the data running on an analog computer. Legal issues. See also, software patents. For a general overview of the patentability of software, including computer-implemented algorithms. Algorithms, by themselves, are not usually patentable. In the United States, a claim consisting solely of simple manipulations of abstract concepts, numbers, or signals does not constitute processes USPTO 2006, and hence algorithms are not patentable, as in Gottschalk v. Benson. However, practical applications of algorithms are sometimes patentable. For example, in Diamond v. Deere, the application of a simple feedback algorithm to aid in the curing of synthetic rubber was deemed patentable. The patenting of software is highly controversial, and there are highly criticized patents involving algorithms, especially data compression algorithms, such as Unisys LZW patent. Additionally, some cryptographic algorithms have export restrictions. See export of cryptography. Etymology. The word algorithm or algorithm, in some other writing versions, comes from the name al-khwrizm, pronounced in Classical Arabic as al-khwayritmi. Al-khwrizm. Persian, c. 782-850, was a Persian mathematician, astronomer, geographer, and a scholar in the house of wisdom in Baghdad, whose name means the native of Khwarizm city, that was part of the Greater Iran, during his era, and now is in modern-day Uzbekistan. About 825, he wrote a treatise in the Arabic language, which was translated into Latin, in the 12th century under the title Algoritmi Numero Indurum. This title means algoritmi on the numbers of the Indians, where algoritmi was the translator's Latinization of al-Khwarizmi's name. Al-Khwarizmi was the most widely read mathematician in Europe, in the late Middle Ages, primarily through his other book, The Algebra. In late medieval Latin, algorithmus, the corruption of his name, simply meant the decimal number system. That is still the meaning of modern English algorithm. In 17th century French the word's form, but not its meaning, changed to algorithm. English adopted the French very soon afterwards, but it wasn't until the late 19th century that algorithm took on the meaning that it has in modern English. Alternative etymology claims origin from the terms algebra in its late medieval sense of Arabic arithmetics and arithmos, the Greek term for a number, thus literally meaning Arabic numbers, or Arabic calculation. Algorithms of al-Khwarizmi's works are not meant in their modern sense, but as a type of repetitive calculus. Here is to mention that his fundamental work known as Algebra was originally titled The Compendious Book on Calculation by Completion and Balancing, describing types of repetitive calculation and quadratic equations. In that sense, algorithms were known in Europe long before al-Khwarizmi. The oldest algorithm known today is the Euclidean algorithm, see also extended Euclidean algorithm. Before the coining of the term algorithm, the Greeks were calling them antipharesis, literally meaning anti-subtraction, or reciprocal subtraction. Further reading here and here. Algorithms were known to the Greeks centuries before Euclid. Instead of the word algebra, the Greeks were using the term arithmetica, i.e. and Diophantus works, the so-called father of algebra. See also Wikipedia's articles Diophantine equation and Adoxo. History, development of the notion of algorithm. Origin. The word algorithm comes from the name of the 9th century Persian mathematician Abu Abdullah Muhammad ibn Musa al-Khwarizmi, whose work built upon that of the 7th century Indian mathematician Brahmagupta. The word algorithm originally referred only to the rules of performing arithmetic using Hindu-Arabic numerals, but evolved via European Latin translation of al-Khwarizmi's name into algorithm by the 18th century. The use of the word evolved to include all definite procedures for solving problems or performing tasks. Discrete and distinguishable symbols. Tally marks. To keep track of their flocks, their sacks of grain, and their money, the ancients used tallying, accumulating stones or marks scratched on sticks, or making discrete symbols in clay. Through the Babylonian and Egyptian use of marks and symbols, eventually Roman numerals and the abacus evolved. Dilson, p. 1641. Tally marks appear prominently in unary numeral system arithmetic used in Turing machine and post-Turing machine computations. Manipulation of symbols as placeholders for numbers, algebra. The work of the ancient Greek geometers, Euclidean algorithm, the Indian mathematician Brahmagupta, and the Persian mathematician Al-Khwarizmi, from whose name the terms algorithm and algorithm are derived, and Western European mathematicians culminated in Leibniz's notion of the calculus ratiocinator, ca. 1680. A good century and a half ahead of his time, Leibniz proposed an algebra of logic, an algebra that would specify the rules for manipulating logical concepts, in the manner that ordinary algebra specifies the rules for manipulating numbers. Mechanical contrivances with discrete states. The clock. Boulder credits the invention of the weight-driven clock as the key invention of Europe, in the Middle Ages, in particular the Verge escapement. That provides us with the Takandak of a mechanical clock. The accurate automatic machine led immediately to mechanical automata beginning in the 13th century, and finally to computational machines, the difference engine, and analytical engines of Charles Babbage and Countess Ada Lovelace, mid-19th century. Lovelace is credited with the first creation of an algorithm intended for processing on a computer, Babbage's analytical engine, the first device considered a real Turing complete computer instead of just a calculator, and is sometimes called history's first programmer. As a result, though a full implementation of Babbage's second device would not be realized until decades after her lifetime. Logical Machines 1870. Stanley Jevons' Logical Abacus and Logical Machine. The technical problem was to reduce Boolean equations, when presented in a form similar to what are now known as Carnot maps. Jevons, 1880, describes first a simple abacus of slips of wood furnished with pins, contrived so that any part or class of the logical combinations can be picked out mechanically. More recently, however, I have reduced the system to a completely mechanical form, and have thus embodied the whole of the indirect process of inference in what may be called a logical machine. His machine came equipped with certain movable wooden rods, and at the foot are 21 keys, like those of a piano, etc. With this machine he could analyze a syllogism, or any other simple logical argument. This machine he displayed in 1870, before the Fellows of the Royal Society. Another logician, John Vin, however, in his 1881 Symbolic Logic, turned a jaundiced eye to this effort. I have no high estimate myself of the interest or importance of what are sometimes called logical machines. It does not seem to me that any contrivances at present known, or likely to be discovered, really deserve the name of logical machine. See more at algorithm characterizations. But not to be outdone, he too presented a plan somewhat analogous, I apprehend, to Professor Jevons' abacus, and again, corresponding to Professor Jevons' logical machine. The following contrivance may be described. I prefer to call it merely a logical diagram machine, but I suppose that it could do very completely all that can be rationally expected of any logical machine. Jacquard loom, Hollerith punch cards, telegraphy, and telephony. The electromechanical relay, Bell and Newell, 1971, indicate that the Jacquard loom, 1801, precursor to Hollerith cards, punch cards, 1887, and telephone switching technologies were the roots of a tree leading to the development of the first computers. By the mid-19th century, the telegraph, the precursor of the telephone, was in use throughout the world. Its discrete and distinguishable encoding of letters as dots and dashes a common sound. By the late 19th century, the ticker tape, ca. 1870s, was in use, as was the use of Hollerith cards in the 1890 U.S. Census. Then came the teleprinter, ca. 1910, with its bunched paper use of Bodo code on tape. Telephone switching networks of electromechanical relays, invented 1835, was behind the work of George Stibitz, 1937, the inventor of the digital adding device. As he worked in Bell Laboratories, he observed the burdensome use of mechanical calculators with gears. He went home one evening in 1937 intending to test his idea. When the tinkering was over, Stibitz had constructed a binary adding device. Davis, 2000, observes the particular importance of the electromechanical relay, with its two binary states open and closed. It was only with the development, beginning in the 1930s, of electromechanical calculators using electrical relays that machines were built having the scope Babbage had envisioned. Mathematics during the 19th century, up to the mid-20th century. Symbols and rules, in rapid succession. The mathematics of George Boole, 1847, 1854, Gottlob Frege, 1879, and Giuseppe Peano, 1888-1889, reduced arithmetic to a sequence of symbols manipulated by rules. Peano's The Principles of Arithmetic, presented by a New Method, 1888, was the first attempt at an axiomatization of mathematics in a symbolic language. But Hegenert gives Frege, 1879, this kudos. Frege's is perhaps the most important single work ever written in logic, in which we see a formula language, that is a lingua characterica, a language written with special symbols for pure thought, that is, free from rhetorical embellishments, constructed from specific symbols that are manipulated according to definite rules. The work of Frege was further simplified and amplified by Alfred North Whitehead and Bertrand Russell in their Principia Mathematica, 1910-1913. The paradoxes. At the same time, a number of disturbing paradoxes appeared in the literature, in particular the Brawley-Forti paradox, 1897, the Russell paradox, 1902-03, and the Richard paradox. The resultant considerations led to Kurt Gödel's paper, 1931. He specifically cites the paradox of the liar, that completely reduces rules of recursion to numbers. Effective calculability, in an effort to solve the Entscheidungs problem defined precisely by Hilbert in 1928, mathematicians first set about to define what was meant by an effective method or effective calculation or effective calculability, i.e., a calculation that would succeed. In rapid succession the following appeared: Alonzo Church, Stephen Kleene, and J. B. Rosser's Calculus. A finely honed definition of general recursion from the work of Gödel acting on suggestions of Jacques Herbrand. Compare Gödel's Princeton Lectures of 1934, and subsequent simplifications by Kleene. Church's proof that the Entscheidungs problem was unsolvable. Emil Post's definition of effective calculability, as a worker mindlessly following a list of instructions to move left or right through a sequence of rooms, and while they either mark, or erase a paper, or observe the paper, and make a yes-no decision about the next instruction. Alan Turing's proof of that the Entscheidungs problem was unsolvable by use of his automatic machine, in effect almost identical to Post's formulation. J. Barclay Rosser's definition of effective method in terms of a machine. S.C. Kleene's proposal of a precursor to Church thesis, that he called Thesis I, and a few years later Kleene's renaming his thesis Church's Thesis 87, and proposing Turing's thesis. Emil Post, 1936, and Alan Turing, 1936-37, 1939. Here is a remarkable coincidence of two men not knowing each other, but describing a process of men as computers working on computations, and they yield virtually identical definitions. Emil Post, 1936, described the actions of a computer human being as follows. Two concepts are involved, that of a symbol space in which the work leading from problem to answer is to be carried out, and a fixed unalterable set of directions. His symbol space would be a two-way infinite sequence of spaces or boxes. The problem solver or worker is to move and work in the symbol space, being capable of being in, and operating in, but one box at a time. A box is to admit of but two possible conditions, i.e., being empty or unmarked, and having a single mark in it, say a vertical stroke. One box is to be singled out and called the starting point. A specific problem is to be given in symbolic form by a finite number of boxes, i.e., input being marked with a stroke. Likewise, the answer, i.e., output, is to be given in symbolic form by such a configuration of marked boxes. A set of directions applicable to a general problem sets up a deterministic process when applied to each specific problem. This process terminates only when it comes to the direction of type C, i.e., stop. See more at Post-Turing machine. Alan Turing statue at Bletchley Park. Alan Turing's work preceded that of Stibitz, 1937. It is unknown whether Stibitz knew of the work of Turing. Turing's biographer believed that Turing's use of a typewriter-like model derived from a youthful interest. Alan had dreamt of inventing typewriters as a boy. Mrs. Turing had a typewriter, and he could well have begun by asking himself what was meant by calling a typewriter mechanical. Given the prevalence of Morse code and telegraphy, ticker tape machines, and teletypewriters, we might conjecture that all were influences. Turing, his model of computation is now called a Turing machine, begins, as did Post, with an analysis of a human computer that he whittles down to a simple set of basic motions and states of mind. But he continues a step further and creates a machine as a model of computation of numbers. Computing is normally done by writing certain symbols on paper. We may suppose this paper is divided into squares, like a child's arithmetic book. I assume then that the computation is carried out on one-dimensional paper, i.e., on a tape divided into squares. I shall also suppose that the number of symbols which may be printed is finite. The behavior of the computer at any moment is determined by the symbols which he is observing, and his state of mind at that moment. We may suppose that there is a bound b to the number of symbols or squares which the computer can observe at one moment. If he wishes to observe more, he must use successive observations. We will also suppose that the number of states of mind which need be taken into account is finite. Let us imagine that the operations performed by the computer to be split up into simple operations which are so elementary that it is not easy to imagine them further divided. Turing's reduction yields the following. The simple operations must therefore include a. Changes of the symbol on one of the observed squares. B. Changes of one of the squares observed to another square within L squares of one of the previously observed squares. It may be that some of these changes necessarily invoke a change of state of mind. The most general single operation must therefore be taken to be one of the following. A possible change of symbol together with a possible change of state of mind. B. A possible change of observed squares together with a possible change of state of mind. We may now construct a machine to do the work of this computer. A few years later, Turing expanded his analysis, thesis, definition, with this forceful expression of it. A function is said to be effectively calculable if its values can be found by some purely mechanical process. Though it is fairly easy to get an intuitive grasp of this idea, it is nevertheless desirable to have some more definite, mathematical expressible definition. He discusses the history of the definition pretty much as presented above with respect to Gödel, Herbrand, Klein, Church, Turing, and Post. We may take the statement literally, understanding by a purely mechanical process one which could be carried out by a machine. It is possible to give a mathematical description, in a certain normal form, of the structures of these machines. The development of these ideas leads to the author's definition of a computable function, and to an identification of computability with effective calculability. We shall use the expression computable function to mean a function calculable by a machine, and we let effectively calculable refer to the intuitive idea without particular identification with any one of these definitions. J. B. Rosser, 1939, and S. C. Klein, 1943. J. Barclay Rosser defined an effective mathematical method in the following manner, italicization added. Effective method is used here in the rather special sense of a method each step of which is precisely determined, and which is certain to produce the answer in a finite number of steps. With this special meaning, 3 different precise definitions have been given to date. His footnote number 5, see discussion immediately below. The simplest of these to state, due to Post and Turing, says essentially that an effective method of solving certain sets of problems exists if one can build a machine which will then solve any problem of the set with no human intervention, beyond inserting the question, and, later, reading the answer. All 3 definitions are equivalent, so it doesn't matter which one is used. Moreover, the fact that all three are equivalent is a very strong argument for the correctness of any one. Rosser 1939-225-6. Rosser's footnote number 5 references the work of 1. Church and Klein, and their definition of definability, in particular Church's use of it in his An Unsolvable Problem of Elementary Number Theory, 1936, 2. Herbrand and Gödel, and their use of recursion, in particular Gödel's use in his famous paper on formally undecidable propositions of Principia Mathematica and Related Systems I, 1931, and 3. Post, 1936, and Turing, 1936-7, in their mechanism models of computation. Stephen C. Klein defined as his now famous thesis I known as the Church-Turing thesis. But he did this in the following context, boldface and original. 12. Algorithmic theories. In setting up a complete algorithmic theory, what we do is to describe the procedure performable for each set of values of the independent variables which procedure necessarily terminates, and in such manner that from the outcome we can read a definite answer, yes or no, to the question, is the predicate value true? Klein 1943-273. History after 1950. A number of efforts have been directed toward further refinement of the definition of algorithm, and activity is ongoing because of issues surrounding, in particular, foundations of mathematics, especially the Church-Turing thesis, and philosophy of mind, especially arguments around artificial intelligence. For more, see algorithm characterizations.